Josh has 16 years of experience as a practitioner in analytical sciences with emphasis on machine learning and statistical applications. He will be presenting a talk titled Machine Learning on Distributed System. Please join me in welcoming Josh.
Great, thanks for showing up today. Before the lights go down, which they might in a second, show of hands, how many of you guys use R or Python or SAS or SPSS, something like that? You use that? Okay, cool. How many Spark? Okay, H2O? Okay, all right. So that is about what I would expect. About everybody has some experience with what I call single node. They can run in parallel, but they run in single node machine learning applications like R, SPSS, SAS, Python. When you get into the world of big data, which is what we're talking about at this conference, pretty soon, if you haven't already, you're going to hit a bottleneck with those systems. Either it's going to be you run out of memory. How many of you have got OOM errors in R or Python or Spark? Yeah, that's a lot of us have that problem. You're going to run out of memory. You're going to run out of the ability to do high concurrent workloads. So if you have 3 or 4 data scientists working at the same time, it's not feasible on single node systems. So in the past 6 years, I've been working with distributed systems, similar to Spark, but a little bit different. The systems I've been working with have been in databases. And I found it interesting that a lot of the data science community is not really aware of what's possible with machine learning inside of distributed databases. And there are definitely some pros and cons to when you would want to use Spark, when you would want to use something in a database, when you would want to use R, when you would want to use Python. So my talk today is talking about that from kind of a technical standpoint, maybe an architecture a little bit standpoint, but also a business case standpoint. When do you do pipelines in each of those systems? So this first slide here just sets the stage. I'm not going to spend too much time talking on it. I've got a lot of material. I want to get through it quickly. Make sure we get to the meat. But data is exploding. And if you haven't hit that wall already, you're going to. When you get into distributed systems like Spark, and like some of the other distributed systems I'm going to talk to you today, the math is actually different. So first of all, a distributed system is a cluster of machines. You've got 3, typically it's 3. If you get bigger problems, you've got 4, 5, 6, even hundreds of compute nodes all stitched together that can run your machine learning algorithms in parallel across all those nodes. So you've got distributed across the nodes and in parallel on every node. So the math is different. I'm talking today about pre-built machine learning functions, not just development environments. So I might leave some things out that are development environments. And when I talk about big data, I'm talking about billions of rows and hundreds of columns. So that's where, in my experience, I start to hit walls with things like R and Python. So this is a typical industry analytical quadrant where they look at different systems and evaluate them. And an interesting question is, how many of these run distributed, meaning across 3, 4 nodes? How many of these can you do large-scale compute machine learning on? And the answer is not many. Maybe only 1 or 2 of those up there are actually distributed. Let me show you the list. And this is, again, well, not again, but I'll be saying this again and again. This is a lot of what I've seen in my experience over the past 16 years, and especially the past 10 years I've been focusing on distributed systems. These are the distributed players for machine learning at scale. You might argue that there are a couple more here and there that are just now coming onto the scene, but these are really the established ones that I've been familiar with and that I know about. So you've got Spark, which a lot of you were familiar with, H2O, which you might or might not be familiar with, and then Revolution Analytics has changed their name a couple times, but they got bought by Microsoft. So they run distributed. And then these last 3 you might or might not have been familiar with in the past. MadLib is a distributed data science library built out of Berkeley to be able to run in database. Greenplum is a database that uses MadLib most frequently, and they have made it popular. Vertica, who's the company I work for right now, has built their own in-database distributed machine learning library. And then a company called Fuzzy Logics, which you probably haven't heard of. but they do something similar to MATLib. It's a distributed machine learning library for databases, and Netezza has made that one popular. So let me break down these 6 into 2 groups, and then I'm going to compare and contrast these 2 groups for the rest of the talk. And I'm going to use these little icons so that we can kind of mentally remember which 2 are which. Both of them are distributed. MPP, if you're not familiar with that, is massively parallel processing. It just means distributed. It means lots of nodes all running at the same time, like a supercomputer. So distributed analytic compute engines, you've got Spark, H2O, and Revolution. They kind of stand on their own. They're by themselves. They're self-contained. You can put them on HDFS or Hadoop. You can put them on Amazon in the cloud. You can put them on your laptop. They'll run on your laptop. They'll run on a cluster of just commodity hardware. So they stand alone. They're generic to any storage layer. Then over here, you've got the MPP analytic data marts. These are first and foremost their databases. So they have some pros and cons that come with being a database, which we'll talk about in a minute. But they also run distributed, and they have built-in machine learning libraries that you access via SQL versus other APIs with a computer environment. So remember from the rest of the talk, the yellow polygon is the data marts. We're talking about databases there. Again, distributed, really high throughput. And then the purple polygon are the compute engines. All right, I'm not going to spend too much time here, but if you're not familiar with Spark, here's just a couple of kind of architecture diagrams to kind of let you get comfortable with it a bit. Like I said, I'm going to use Spark as the poster child for the compute engines, and I'm going to use Vertica as the poster child for the data marts. Okay? So Spark has a lot of infrastructure built around it, or I should say a lot of applications that can plug into it very easily. You've got development environments. It can plug into BI tools. It usually is most popularly sits on HDFS, but it doesn't have to. It can be on the cloud too. The cloud's the other place that is very popular for it to sit. So Hadoop, HDFS, cloud, Amazon EC2. You've got different interfaces. You do have some SQL, although typically it's not standard SQL. Spark R, Java, PySpark, and Scala. So the point of this talk isn't to get totally into Spark, so I'm going to leave that there. Here are a couple of bullet points to keep in mind with some of just the general advantages of going with a distributed compute engine like Spark, H2O, or Revolution. They use commodity hardware, so that means the servers you buy, if you want to do it on-prem, are a little bit cheaper. They adapt to any storage location. They can take any type of data. You can really get customized with your ingest or data prep. And they have some built-in data discovery tools, so you can do some visual analytics. You can customize all your analytics via these programming APIs here. Okay, so you can get really, really just specific on what you want to do with your analytics. And in my opinion, they have the deepest and widest libraries available. All right, so that's the compute engines. Now I'm going to jump to the data marts. We'll have some bullet points for those, and then we'll start to compare and contrast them. So here's the data marts. I'm going to use Vertica as my poster child for the data marts because that's the company I work for. They interact with Spark and the open source world. They also interact with the BI world over on the other end. And they also have different APIs, R, Java, Python, but of course, being a database, the most popular API that they like to use is SQL. And they're better at SQL than the compute engines or compute environments because they're usually SQL standard. For example, Vertica is SQL 99 compliant. Inside of these databases, those libraries like MATLib, Vertica's library, and Fuzzy Logics, they have lots of different algorithms that are kind of pre-packaged, ready to go. So you got geospatial, time series, machine learning, pattern matching, text analytics, and many others. And let's look at some of the bullet points for these. And here's where I really start to make the point of this talk, is that if you're a data scientist or an analyst and you've never thought about doing some of your more advanced analytics in a database, there are definitely some times when that's going to be the way you want to go. They also use commodity hardware like the other stuff, but they have built-in data storage. There's a lot of advantages to having a built-in data store. We'll get into that a little bit. They have advanced storage techniques. And this is a claim I make, which you might raise your eyebrow at, but they have the fastest analytics at scale available, faster than Spark. I'll show you some benchmarks here in a second. The fastest streaming analytics available. A lot of these faster claims come from the fact that you've got the data stored tied to the compute engine. And so the developers can do some really neat stuff with optimizing throughput and analytics at scale. They use disk when needed, so you don't have the OOM errors. You don't run risk of running out of memory because they can spill the disk, because again, they're tied to the data store. Because it's SQL, you have really short development times. So you can get to market real fast. You can iterate models really quick, and there's some advantages to that. This is a huge one, actually. These next two are really big when people are making decisions about what type of platform to go with for machine learning. All the enterprise features come out of the box. If you're a data engineer and you've tried to do security on Hadoop and high availability and disaster recovery and resource management and keeping track of users and let's look at the user logs, that's a lot of work on Hadoop. The database, it comes out of the box because that's how databases were built from the ground up. Concurrency is another big one. If you've ever tried to do high concurrency in Spark, it's really hard. It takes a lot of data engineering to manage yarn and to manage memory spaces, and you run the risk of running out of memory, and you can't really be flexible too much with that memory. A database, again, has that high concurrency built in from the ground up. It thinks about that from the beginning. The infrastructure is built that way. So you can have, I've run tests with 40 data scientists running very large machine learning algorithms in Poduska, and it runs at no problems. You have very high concurrency, no memory issues. And then it handles all the enterprise ad hoc discovery and BI. Okay, here's the benchmark. This is Vertica. I don't have the versions on here. This is, I believe, Vertica 7.2 versus Spark 2.0. So it's a recent version of Spark. If you want to follow me later, I can give you all the details behind these benchmarks. What you're looking at is basically, just look at the last column, if you will. That's a billion rows. Each of these have 100 columns of data. And you've got k-means, linear regression, logistic, and naive Bayes. Basically, the key takeaway is if you're doing k-means in Spark, you're about a little bit over 2 hours versus 7 minutes in Vertica. And the linear regression Spark's a little bit faster. Let's look at this one here, naive Bayes. 418 minutes, that's almost a work day. That's pretty much 8 hours versus an hour and a half inside of Vertica. So this hopefully starts to let you see the advantages in performance that you can get on really large data sets if you're working with one of those data marts versus a compute environment. Now, you don't always want to go with the data mart. There are times you want to do the compute environment. Let me walk through that a little bit. I'm going to skip this slide for the sake of time. And check my time. Okay, doing good. This is a little diagram I put together based on what I've seen over the past couple decades working with customers as to areas of consideration for when they choose a machine learning platform. So I've got 4 groups, and in each of those 4 groups, I've got 3 little bubbles. So data demands, organizational resources, accuracy requirements, and deployment configuration. So the next slides, I'm going to have a slide for data demands, and I'm going to talk about those 3 bubbles. Organizational resources, 3 bubbles, and so I have 4 slides diving into each of these. So data demands. And I put a little data mart yellow guy or a little purple compute environment if, in my experience, if that one has an edge in that consideration. So data demands. You talk about size. Again, billions of rows, hundreds of columns, data marts are the place to go. Everything is built in. It's a one-stop shop, load and go. The data's there and it runs faster than something like Spark or H2O. Types of data. If it's structured, of course, a data mart's going to be better. Both of them, I think, handle logs. In my experience, both handle log data just fine, so I've got an equal sign for that one. Unstructured, that's where the compute environments have an edge, because the databases don't really handle the unstructured data as well. Location, you could argue that these are both equal, because both of them can handle both. But if you're talking about the traditional data stores, the data marts have an edge. If you're talking about the cloud or Hadoop, Spark has an edge just because it's been there longer and the connections are a little bit better. So organizational structure. So first, data demands, that was kind of a wash, about equal between the two. If you're looking at organizational structure, if you have any constraints on the size of your organization, or the depth of skill set in your organization, you really should consider some of those data marts for your data science platform. They control, I mean, your hardware costs are about 1/3 of the compute environments. So if the same analytical application on Spark or on Vertica, about 1/3 of the hardware for Vertica versus Spark. That's a big savings. You don't need as many data engineers and admins to maintain the databases as you do an entire Spark environment. Of course, Spark is open source, and those databases are usually not, so their software costs goes to the compute environments. Support costs are about the same. Headcount, definitely, it's easier, you just kind of deploy this so much easier with the databases, and then the concurrency, as I spoke to earlier, is in favor of the databases. All right, accuracy requirements. So the organizational structure was definitely leaning towards the data marts. If you look at accuracy requirements, it really leans towards the compute engines. And this is, a lot of the times, this is where people say, yeah, I got to use Spark. I can't use anything else. I have to, because I really need depth and variety. But lots of times, if you think about it, your analytical workload really needs that model agility. So think of all the accuracy. So let's think of a project like customer churn, okay? And you've got, let's say, a swimming pool full of accuracy. And if you fill that swimming pool to the top, that's all the accuracy you could squeeze out of that model. Data prep sometimes will get you, that swimming pool will be really full, maybe 95% of the way full. You're not going to get that last little bit, but you can get there quick with data marts, and you can deploy quickly. And sometimes being first to market with 95% of the available accuracy is going to be a better business decision than waiting another year and squeezing out maybe 3% more out of that total available accuracy of that swimming pool model. But if you do need to squeeze out all that accuracy, you've got model depth and model variety are much better with the compute environments, because you can really balance bias and variance trade-off. You can try all different hyperparameters. You can tune the model. And typically the databases don't have as many bells and whistles as the compute environments do. All right, and the last one here is deployment. Generally, it's easier to deploy with these databases because they're built for embedding. There are a lot of what the business calls OEM customers with the databases, where they will buy the database, deploy it as part of an overall solution, and you don't have to maintain it. You just replicate the thing 20, 100, 1,000 times, and it goes. Whereas with something like Spark, each time needs a lot of custom configuration. All right, so in kind of summarizing that, data demands was about equal. Organizational resources definitely bring you back towards the databases. Accuracy brings you towards the compute engines, and the deployment is a little bit leaning towards the databases. So 2 out of the 4, really, databases hit it really well. And that was surprising to me when I first kind of wrote this down on paper and thought about all the different decision points that customers and organizations go through. Because lots of times we're conditioned to think that things like Spark and H2O and Revolution are the de facto standard. And we don't think that, hey, there might be actually cases where if you're going in database, it's going to be a lot better for your organization. So the last slides I have here are on kind of a decision flow. So this is the same data, the same slide as the previous one, but each of the bullet points are either up high if they favored data marts, or down low if they favored compute engines, and in the middle if it was the equal sign. And the way my mind's thinking with a slide is, you would go along, and this is kind of like a decision flow, and you see whether you end up lower or higher on this kind of decision flow as you go along. So I've got a couple of examples, 2 examples. One of them, I was working with a large credit card company. They were doing a real-time transactional fraud system. So it's a very large company. Think something like American Express or Capital One or something like that. And they were evaluating doing their data science in database versus on something like Spark. So as they go through here, I've got little footprints that kind of mark where their minds are at. So they had lots of data. Most of it was structured. Some of it was in the cloud. So they started up really high. They started to move down lower. So here they're kind of leaning towards the data marts, and now they're starting to go more towards something like Spark. As you move along, they really were sensitive to software costs, so that brings them down closer to the compute environment decision. Headcount they didn't care about. They had tons of engineers, right? It's a large credit card company. They got lots of data engineers. But they do need concurrency. Where it really starts to drop down, and like they're like, man, we got to use Spark, was on model accuracy. So on model accuracy, they needed to squeeze out every 0.01% of accuracy they could out of this model. And they didn't care if it took them another year to do that, because they already had something in production. They just wanted to get better and better and better. So for that reason, their thought process drops them down closer to Spark. And as you look at the last few with deployment, again, they've got an army of coders. They can code, they can build it in Spark and code it in C++ and deploy it, no problem. So for them, the right decision was Spark. I was actually working for a different database company at the time. When I talked to these guys, I was like, hey, based on all your requirements, keep using the database for BI and for ad hoc discovery. You should be doing your data science in Spark, right? It's not always a good fit to do your data science in the database. So let me show you one example where it was a good fit. This was a mid-sized network analytics and cybersecurity company that I worked with recently with Poduska. So they also had lots of data. It was all structured, and they didn't really care about the cloud too much. Everybody wants to control software costs, so they kind of leaning toward, at least were looking at open source a little bit, but they did not have an army of engineers. They were more of a mid-sized company. They don't have that depth. They can't throw money and bodies at the problem. They did want model accuracy, and that was important, but they also wanted to deploy really quickly. So when you deploy really quickly and you are looking to be able to get to the market fast, and you want to catch most of the problems with network security, but you're never going to catch them all. Even if you spend a year trying to build the perfect model, you're never going to catch every malicious actor. So for them, combining their data science platform with their existing BI and ad hoc data mart made a whole lot of sense. They could save a lot of money by not having to install Hadoop, or if they do install Hadoop, they use it for their cold storage. And everything hot and everything data science, all your concurrency, your data science workloads are all right in the database. So that made a lot of sense for them. All right, I'm moving through quickly, so this is great. So this is my last slide. It's kind of a summary slide. And the point here is that there are definitely times, and maybe most of the time, you're going to be doing both. You'll have both a data mart and a generalized compute engine. They can live together. So in this architecture diagram, here you would think your MPP, here you would have your Netezza, your Poduska, your Greenplum, and over here you would have your Spark, your H2O, or your Revolution. Both of them can interact with the entire ecosystem. But again, some of the key takeaways that I'm hoping that you will get from this talk is that are in these bullet points on the side here. And that is that most organizations already have both of these. So think about your analytical needs and think about where you want to, how many physical servers you want to dedicate to the problem, and where do you want your hot and cold data to live. If your analytical pipeline, your analytical use case could be served by the data science inside of a database, why would you invest so much time and so many cycles into really fine-tuning an open source platform if you already have the database and it can work right there for you? The last bullet point there talks about the speed. So if you can use the database, you're going to get much better speed for many of the workloads in Spark, and also you're going to save on the hardware. So it saves about a third of the hardware cost is what I've seen. In addition to that, the data engineers love these last points. The improved security, enterprise features like disaster recovery and high availability, and increased concurrency. I really can't stress enough, if you've ever tried to do Spark in production with other data scientists simultaneously, you know that concurrency is a real big issue. And the databases are a nice solution to solve that. So that's my last slide. One thing that, since I have a minute or two left, One thing I might mention is what type of analytics are available in databases. I can speak specifically to Vertica. So as I mentioned, it doesn't have all the bells and whistles that Spark has, but it has quite a bit. So inside of Vertica today, there's linear and logistic regression, k-means, support vector machines, naive Bayes, and random forest, and a wide variety of time series and data preparation functions as well. And the beauty of it is it's all available via SQL. So as you start to do your data science workloads and pipelines, you'll find that you can code really fast, iterate really fast, and try to get the best model accuracy you can out of that. So with that, I think I'll end there and see if we have any questions.
Yeah. For newer problems, connected data, for the newer problems, you are looking at mostly connected data, and graph solutions play a very vital role. Where do you see them on this architecture level?
Yeah, so with connected data and with graph solutions, so Spark has a graph API to it, and it can do graph problems. Databases, because of their kind of relational structure, can do very well with graph problems as well. So who's related to who, what are the networks, what are the edges, what are the connections. Databases are set up nicely for that. So really either of the solutions can handle that. Yeah, well, there's a couple.
So there was a slide where you showed how with the increasing number of records, like Spark had a sudden spike in like performance time that it takes to converge. Is that holding the same number of nodes, or how does it smooth out if you increase?
Yeah, I'll go back to that slide. It's the exact same number of nodes. It was a 3-node AWS cluster for both of the benchmark comparisons, I believe. Let me go back to it here. Build slide takes a minute. So yeah, everything was kept the same, and the only thing that changed were the number of rows that we fed. So we did several iterations of the experiment with different number of rows. That's why the graph moves. It's getting more data. And this is model building, by the way. This is how long does it take to build, k-means, Bayes. It's not model scoring.
So we've done a lot with Spark, but we've also used SAS and SPSS and other single node tools. So for the purpose of training a model, what is the argument for training it over 1 billion rows when you can sample, when you can train a model on a statistically representative sample, which has been around for decades? I just don't see that.
Yeah, that's an age-old argument, usually between academia and industry is, well, how come you can't just sample? There are certain applications, for example, anomaly detection, or any type of really low frequency applications where you have to do tricks like balancing the data if you don't have enough of it. If you take 1 billion rows, you might have enough of a signal to actually go find it. Or if you have 1 billion rows, when you balance the data, you can just throw away some of the zeros for the labeled data for the target variable and keep some of the ones. So, I personally have thought about that before, and I'd love to do some type of experiment on that and see how much accuracy there actually is gained. I'm sure there's probably papers out there on that we could probably Google and look it up. But a lot of people argue today, if you have the data, why not use it? So, and there are systems out there that can do it now. All right, great. Thanks, guys.